Okay, shielding. So this is, you probably also remember from general chemistry, and this is how the electrons in outer orbitals or even energy levels have a little bit lower attraction towards the nucleus. So again, if we stick with a straightforward case where we have a filled 1s shell, that would be that the effective nuclear charge, or ZF, would be equal to Z minus 2. If you're looking at a filled s and p orbital, that would be Z minus 8. So let's look at what's going on here. So shown here are some plots of the radial wave functions for several different combinations of N and L. So for a 1s electron, we can see that the probability shell at about 95% is when the radius is equal to about 3 times the Bohr radius. So if we integrate that area shaded here in red, you can see that's a 95% probability interval, and then you can see where that is in space. Now, if we look at a 2s electron, we'll see that it has a pretty large probability of being inside the orbit, the 95% interval for 1s. So this is suggesting that you have a pretty appreciable probability of a 2s electron actually being within a 1s orbital. So this is an example of penetration, where the electron isn't quite as shielded as you would expect, just given that very simplistic Bohr approach where you have these concentric orbitals. Here we see that we actually have some shape to the orbitals, and that appreciable probability actually lies within the different ones. Now, when you look at these plots, be very careful. Make sure you pay attention to the x-axis. As you'll see, there's some changes in the scale. Okay, so let's look at a 3p electron here. So with the 3p electron, you can see that there is still a appreciable probability inside the 1s, but you can tell it is far less smaller. But you can imagine that with the 2s electrons, 2p electrons, all that stuff, is that you wind up with very different with a very different penetration, and that, say for example, a 2p electron has a pretty high chance of being inside a 3s electron, and likewise a 3p electron has a pretty good chance of being inside a 2p electron. So this simple model of shielding from the Bohr radius doesn't quite cut it, and we need to actually pay attention to the radial wave function when we start thinking about what these effective nuclear charges are. So even if they're a closed shell, you can still have extensive penetration. Okay, so again, here are the plots of radial wave functions for a few different combinations of N and L. Okay, shielding. So here we have those same plots that we showed before of the different radial wave functions for various combinations of P and L. So what we can see is that the shielding is modified by penetration of outer electrons, that's electrons with higher principal quantum numbers, into the region occupied by the lower quantum number electrons. And don't forget, the lower quantum number electrons are more energetic. So remember, they're lower compared to the vacuum level than electrons with higher quantum numbers. So unfortunately, this is an example of where the orbital approximation isn't quite perfect, because the orbital approximation basically treats them as non-interacting, and that doesn't make any difference if they're there or not. And in this most simplistic way is that the effective nuclear charge will smoothly vary with the occupation of the lower lying energy states. But as we're seeing, even an electron in a fairly high quantum number can sometimes feel the nucleus that, say, a 1s electron is feeling. So the effective nuclear charge is not as simple as subtracting the number of closed shell electrons in lower energy levels. So again, the key is that, well, we're looking at how electrons in different orbitals feel the nucleus. And we can see here that looking at comparing 3s and 3p, that principal quantum number isn't the only criteria. Turns out that the angular momentum quantum number also makes effect. So again, looking at the difference between 3s and 3p electrons, we'll see that 3p electrons have a pretty good probability of being within the orbital that you would expect for 3s electrons. Now, let's not forget another thing, that when an orbital gets filled, say the 3s electron gets filled, what happens is this actually contracts the orbital because you have the spin pairing. So if you think about it, the volume occupied goes down a little bit, and therefore the penetration of the 3p electrons into the 3s goes down. So this is, we have several different things going on as you go across the periodic table. So the take-home message is, of course, that the 3p electron feels the nucleus less once the 3s is filled. So in the very slow handwriting here, this means that we have decreased penetration, and therefore the shielding was more important. So this is why this is an example of how the filling or half filling of orbitals is important. So as you can imagine, we're going to come back to some more general chemistry concepts. Now, again, don't forget the most important thing is the orbital approximation is pretty good. But we're just going to look at, how it isn't quite perfect. But we can also use this to understand some of the periodic trends and why electrons fill the way they do. So, you probably recall the Aufbau principle, one of the few principles not named after somebody. It's just a German word. Bonus points for if you know what Aufbau means. Now, if you remember, this is a guideline that you prefer to either half fill or fill an orbital, meaning you have 1s1, 2p3, 3d5, something like that, 1s2. Anything where there's a tendency where as you're going across the periodic table is that you'll half fill an orbital at the expense of, say, having some random d electron making the sixth one to pair up an electron, right? Now, what this really is a manifestation of Hund's rule. Now, this is actually named after someone. So what this says, we've already discussed this, where we know the atomic configuration is trying to not have paired spins, because it turns out the maximum multiplicity is what we're looking for. What's multiplicity, you ask? Well, if we already saw a little bit of that, remember the triplet and singlet states? So a singlet state is when you have paired electrons. And remember, there's only one way to do that. Whereas a triplet state is where you have the spins going the same direction. So in that case, if you recall, there's three different ways to arrange that. So this kind of sounds like our good friend entropy, right? The more ways you can do a configuration, the more favorable it is. Maybe it's something like that, but it's a good guideline that systems tend to favor multiple ways to configuration. Now, what Hund's rule tells us is that, well, if you can have all your spins aligned, that's going to be a more favorable orientation. Again, energy depends on the total quantum number, not necessarily on the spins. But that's total energy. Remember, when we're looking at the radial wave function, all this penetration, everything, what that's telling us is the potential energy. So we always have this modulation of kinetic and potential energy, where if you have more energy and potential energy, when you do something with that electron, that means it's going to have more energy because you don't have that energy wasted as kinetic. Pretty neat, eh? So, atoms in general prefer the spins to be aligned, meaning that as you go across, say, your d orbital, you do 5 electrons all pointing in the same direction. All their spins are aligned. Now, this is, again, a preference. This is what it wants, but it's a good way of going about it. Now, this means that the ground state, or minimum energy configuration, has all the spins aligned. And again, total energy is set by the quantum number. We're looking at the potential energy here. So let's look at an example. Here's a generic d orbital with the 5 different energy levels, and we first put in the 5 electrons so they're all spin aligned, and then as we add the electrons, we have them going the other way to pair the spins up. So that's what Hund's rule is. Now, as you recall, if you have, say, 3d and 3s electrons, you'll have configurations where it'll be 3s1 and 3d5. And that's where you have this, because the alignment of the electrons spins is the big deal, is that you have apparent removal of an s electron and promotion to a d. Well, that's not promotion, because again, principal quantum number, but we'll take the one electron out of the s orbital and use it to half fill the d orbital. Now we have all 6 electrons with the same spin. Again, that's what it tends to do. That's what it wants to do. Sometimes it's enough to make a difference, sometimes it's not. Again, this is just one of the shortcomings of the orbital approximation, but it's really not that big of a deal. So you should feel good. Now you've seen these tendencies that you learned about in general chemistry and maybe even before. And now you can see that there is a underlying principle where it all comes down to the wave functions. If you can maximize multiplicities, that's what you're trying to do. So you have more wave functions that you can add together. Okay, so again, orbital approximation is working pretty well. This is just a way of handling things in the context of the orbital approximation. So let's turn our attention for a little bit to look at some other periodic trends. So we'll talk about this one a bit in the class so far, and this is ionization energies. And as you recall, this is the energy required to remove an electron from an atom, or to remove an electron from an ion. So this would be basically going from whatever orbital the electron is in into the vacuum level. And remember, everybody has the same vacuum level. That just means that the electron and the ion or the nucleus or whatever are so far apart that the Coulombic attraction just doesn't matter anymore, and that they're indifferent to each other. Okay, so just a little bit of the nomenclature. So remember, the first ionization energy is to remove one electron, or the first electron. This is going from an atom, that would be going to the +1 ion. Second ionization energy is then removing another electron from it. You can always remove one at a time, and then so on and so forth. You can imagine, third ionization energy, fourth, whatever it winds up being. Now, the ionization energy has a twin, let's say, and that's electron affinity. So this is the tendency of an atom or an ion to want to gain an electron. So you can imagine that most ions that are positively charged will have an electron affinity because they want to have another one. But you also recall that some atoms are perfectly happy to gain another electron. Well, the reason they want to do that, if you remember, you always, we're trying to fill the octet rule. Well, yeah, why not? That's a pretty good way of thinking about it. So let's look at what the sign of the electron affinity, because we know that the ionization energy is always going to be positive. It's a requirement. You need to add the electron to the atom in order to get the electron to go away. So if you add an electron to an atom or an ion, if the energy is the electron affinity will be positive when you add it. That means it's desirable. And if it goes down, that would be that when energy is level, that would be a negative electron affinity. And you can probably imagine how shielding, penetration, and Hund's rule all come into play here, where you would expect atoms with that weakly held, not really feeling the nuclear charge, like all the first column, all those S1 configurations. Well, they feel all those closed nuclear charges. It doesn't have extensive penetration, therefore it's more weakly held. And because there's no more electrons in the open orbital to pair up, Hund's rule doesn't come into play. Then you can imagine the case where, on the other side, fluorine and all them, they can add one more, then they can complete the orbital and fill everybody up. So, and then as you go across the period, you'll see that more and more. Okay, so there's a quick review of what we did in general chemistry. And now let's go back to the spectroscopy. Let's look at what happens when atoms gain or emit a photon. And let's stick with helium. Helium's a nice test case because it's straightforward in that there's only 2 electrons to keep track of, but the rules that we see for helium are applicable to pretty much any other atom, because remember, spectroscopy, you're only exciting 1 electron in the atom, no matter how many electrons there are, and it can only absorb 1 photon. Okay, so here's what we're looking at. We have helium in the ground state, that's 1s2 configuration, and we're adding a photon. Okay, so what do we know? We know one electron was going to get promoted because one electron can absorb one photon, and we have some selection rules. We know that L has to change by plus or minus 1, and concomitantly M sub L has to change by either plus or minus 1, or it can remain unchanged. Well, this is a s electron, so L is equal to 0, so we know that if it gains a photon, the angular momentum can only go up because it's starting out at 0. So we know we can only look at transitions into p orbitals. Not bad. Okay, so one possibility is promotion of a 1s electron into a 2p electron. Another possibility would be promotion of a 1s electron into a 3p electron. Or what about 1s into a 3d electron? Now, which one of these do you think are going to be forbidden, and which one of these are going to be allowed? Well, the 3D, that would be delta L is equal to 2, so that's a forbidden transition. We don't expect that to happen. We haven't said anything about if there are selection rules for principal quantum number. Turns out they're not. It's the angular momentum quantum number that really matters due to spin conservation, because remember the photons spin one particle. So we would expect that both transition from 1s to 2p or 1s to 3p would be allowed. So let's take a look at the transition from 1s to 2p, and let's see what happens to the electron spin. As you can imagine, there's two possibilities. The electron spins can either stay paired, where one is spin up and one is spin down, or the other outcome is that the spins are aligned, meaning that they're both up or both down, or that third case that you only get because of the fact that these are described by wave functions. Now, if we look at what the spins add up to, so if they're paired, meaning one spin up, one spin down, that's 1/2 plus minus 1/2, so that gives s equals 0. That's a singlet. If they're aligned, then it's either minus 1/2 plus minus 1/2 or 1/2 plus 1/2. Either way, you get spin of 1, and that's a triplet. The multiplicity, as we'll see, is equal to 2s plus 1. So when s is equal to 1, it's going to be 2 times 1 plus 1. That gives us 3, therefore a triplet. As you recall, because we have 3 different ways of arranging things, both up, both down, then that funky quantum mechanical combination. Versus a singlet, well, you only have the one way to do it. They're paired together. It's sort of the anti-symmetric combination of the wave functions, because you're subtracting the two together rather than adding them, as you do for the triplet state. Now, okay, so here we're just going to use a little bit of wave function nomenclature. So we're going to use our wave functions as alphas and betas, and then 1s and 2s. This is electron 1, electron 2, and state alpha and state beta. So for the spins, we have the case where either they're in electron 1 is in state alpha, electron 2 is in state alpha. That's both spin up, let's say. Then the other case is beta 1, beta 2, and that's where the electrons are both spin down. Then you have that so-called funky quantum mechanical combination where you're adding the two different combinations together, and then of course you have the 1 over root 2 normalization constant, versus the singlet state where you're subtracting those two combinations. So if you look in either case, you have alpha 1, beta 2, meaning that electron 1 is in state alpha, electron 2 is in state beta. So you'll see that nomenclature. We'll probably see more and more of that, where we just simply use the Greek letters to indicate which set of quantum numbers, which state the electron is in, and then just simply index them by what number they are. Okay. Now, for all 4 of these cases, because these are the difference, remember, we only have 2 electrons here, right? What can possibly be going on? We have the 2 electrons, but we have 4 different ways to arrange the spins, basically. But all these are still a 1s1, 2p1 configuration. They all have the same energy, same penetration, same shielding, all that stuff. But we'll see that you have different ways of arranging the spin. So, what is Hund's rule asking? Well, Hund's rule is saying that there's a general tendency for the spins to be aligned. So why would you expect that to be any different in this case? So we would expect that there would be a slight preference for the triplet state because of the greater multiplicity. Okay, now it's important to note that all this is only for excited state atoms. This is where we have an atom that absorbed a photon, goes from the ground state to some sort of excited state. And we're going to indicate excited states by the little Tinkerbell sign, little asterisk by the atom. It's still an atom. It's not ionized or anything like that, but it has more energy than you would expect from a ground state atom because it absorbed that photon and one of its electrons got promoted to a higher lying energy state. And again, here's the word, higher lying. Because it's promoted, it's closer to the vacuum level, right? That means it's higher in energy with respect to, say, a core electron, but it's closer in energy to running away. The electron is would have a lower decreased ionization potential because it's closer to the vacuum level. Okay, so here's what's going on. Helium absorbs a photon, promotes one of the electrons to, say, a 2p orbital, and then, of course, you eventually have a reverse process where it emits one of these photons, returning it to the ground state. Now, you might be asking, well, how can the spins possibly change? We know spins have to be conserved. Well, don't forget, spins are like magnets. They need to have somebody telling them which way is up. So when they're in the same orbital, because of the Pauli exclusion principle, they know that they have to pair their spins. But when they go to a different orbital, now they don't have that reference point. They don't know anymore if they're supposed to be spin up or spin down, but they do sense this, well, if I can maximize my multiplicity, have my spins aligned, that's what I want to do. I already changed the L or the m sub L quantum number, so why can't the spin quantum number be different? You have to remember, it goes back to a superposition when you take away the pairing. And that's why you're allowed to have spins seemingly change, because now they're no longer in the same orbital.